In December 2024, a processor the size of a dinner plate, cooled to temperatures colder than deep space, ran a sampling calculation in a controlled laboratory in Santa Barbara that every classical supercomputer on the planet would need an impractical stretch of time to replicate. Weeks earlier, and roughly 9,000 kilometers away, a team in Hefei reported a different machine hitting the same classical frontier with a larger qubit count, and by their own analysis, a wider margin of separation from any classical rival. 2 machines, 2 cities, 2 strategies, 1 question. Which of those strategies actually leads somewhere useful? The first bet is on speed. The team at the University of Science and Technology of China, working on the Zuchongzhi line of superconducting processors, holds that demonstrating a computation beyond classical reach, regardless of whether the underlying qubits are error-corrected, is the scientifically and strategically meaningful event. The second bet is on error. Google Quantum AI's Willow chip, announced in December 2024, holds that below-threshold error correction is the only milestone that physics actually requires, because every quantum algorithm with a known advantage over classical computing was designed assuming fault tolerance. What gets weighed here is a vendor claim against a peer-reviewed result, a sampling headline against a threshold crossing, and a fabrication asset against a physics argument in that order, with the odds line moving after each. The shared arena for both bets is a benchmark called random circuit sampling. A quantum processor draws samples from a probability distribution that classical machines cannot efficiently reproduce. Both the Zuchongzhi line and Google Quantum AI have used this benchmark as their primary supremacy demonstration, which makes it simultaneously the measure China leads and the measure Google's team has argued is not sufficient proof of practical utility. It is the field's most contested metric precisely because both sides have staked their headline claims on it. Every weighing below returns to this benchmark, because wherever it moves, the odds move with it. The speed bet opens with a genuine lead on the headline. Successive generations of Zuchongzhi processors, as reported by the USTC group, in a sequence of preprints and publications running through 2024 and into 2025, have produced random circuit sampling results the group's own analysis places beyond classical simulation by margins that grow with circuit depth. The qubit count in the most recent public claims exceeds 100 superconducting qubits, a figure the USTC group has reported in its own publications as a vendor claim rather than an independently reproduced measurement. The trajectory across generations is consistent with a group that has solved fabrication at scale. Each iteration reports more qubits, deeper circuits, and a wider gap to classical machines. The rebuttal to that opening position is one the inventors of random circuit sampling have made themselves. Google's team designed the benchmark specifically because it is hard to simulate classically, not because it resembles any computation anyone wants to run commercially. Crossing the classical threshold on sampling does not transfer to problems in chemistry, materials science, logistics, or finance, which are the domains where quantum advantage would have economic value. The benchmark was built to be a qualifier, and the speed bet is pricing the qualifier as if it were the destination. The field's history compounds this concern. Classical simulation techniques have improved repeatedly in the years since the first supremacy claims, each improvement narrowing the apparent gap without any change to the quantum hardware. As of the first half of 2025, independent teams outside the USTC group have not published reproductions of the specific circuit depths and qubit counts the group has claimed. The results exist primarily in the group's own publications and preprints. That is not a disqualification because the field routinely operates on preprint timelines, but the standard caveat applies with extra weight here. No external team has confirmed the sampling margins at the reported scale. The line on the speed bet moves slightly toward the skeptical read. The lead on optics is real. The lead on confirmed substance is narrower. Now the other side of the ledger prices indifferently. Google published the Willow result in a peer-reviewed journal in December 2024, a distinction that separates it from every preprint-only claim in this comparison. What the paper reported was below-threshold error correction scaling. As the system grew, logical error rates fell rather than rose. That is the first reported demonstration that adding more physical qubits to surface code architecture can actually improve performance rather than compound the noise. Independent quantum information researchers, not affiliated with Google, acknowledged the result as a category advance rather than an incremental scale-up. The peer-reviewed status and the external acknowledgement together move the error bets line upward significantly, not because a useful machine is close, but because Willow cleared a theoretical gate that the Zuchongzhi line has not attempted. Consider what below-threshold scaling means in physical terms. A superconducting qubit holds its quantum state for a window typically measured in fractions of a millisecond, roughly the time a hummingbird's wing takes to complete a single beat. Every gate operation, every error correction cycle, every measurement must be completed inside that window, stacked in sequence with a precision that makes ordinary semiconductor timing look unhurried by comparison. Before Willow, the consensus expectation in the field was that adding more qubits to correct for noise would itself introduce new noise faster than the correction could compensate. The threshold crossing says that expectation can be beaten, at least in a specific surface code configuration, at a specific scale. That is what the physics community is marking as a genuine advance. Here's where the analyst prices a clean loss for the speed bet and prices it flat. On the metric the error bet identifies as the decisive one, below threshold error correction scaling, in a surface code or equivalent architecture, the Zuchongzhi line trails Willow, and the trail is not marginal. The USTC group's publications focus on sampling performance, qubit count, circuit depth, and the gap to classical machines on the random circuit sampling task. The group has not reported a comparable below-threshold scaling result. There's no equivalent peer-reviewed result from the Zuchongzhi line that addresses the error correction threshold. The architectural choices that produce the sampling headline appear to have come at the cost of the error suppression work Willow has now demonstrated. The speed bet loses this category cleanly. The analyst prices it that way and does not immediately win it back. The question that partially reprices the speed bet's origin is why the USTC group ended up on this particular architectural path. The constraint to catalyst dynamic is worth pricing separately. USTC developed its own superconducting fabrication capabilities and qubit designs partly in response to restricted access to leading Western semiconductor and quantum hardware supply chains. That development path optimized for the metrics the group could control: qubit count and circuit depth. A genuine sampling lead emerged as a byproduct of building self-sufficient hardware rather than as a primary design objective. The compounding asset here is real. A fabrication capability that does not depend on Western components and cannot be disrupted by further supply chain restrictions is a strategic durable, not a temporary one. The rebuttal to that asset repricing is also real. Supply chain self-sufficiency is a strategic condition, not a technical advantage. Building domestically is not the same as building toward the architecture the physics requires. The path forced by necessity may have locked in a trajectory optimized for scale and sampling speed at the expense of the error correction depth that Willow has now demonstrated. A lead that originated in constraint, rather than in a deliberate design choice, does not automatically compound in the direction the race requires. The line on the constraint thesis moves modestly toward the speed bet's durability, then gives some of that gain back when the architectural trade-off is priced in alongside the clean loss on error correction. The decisive weighing now. The peer-reviewed publication of Willow's below-threshold scaling result is the single heaviest piece of evidence on the board at this moment. It is the only result in this comparison that has cleared peer review, the only one that addresses the physical condition the field identifies as necessary for fault tolerance, and the only one with external independent acknowledgement as a category advance. On the question of which bet is backed by stronger evidence, the error bet's lead after Willow is not a close call. But the three strongest reasons the error bet could still lose deserve to be priced explicitly. First, the Willow threshold crossing is a demonstration in one specific code configuration at one specific scale, and it has not been reproduced by an independent team building the same architecture from scratch. Peer review validates the analysis of reported data. It does not independently verify the hardware performance on a separate machine. Second, the gap from a below-threshold demonstration to a fault-tolerant machine running economically valuable algorithms is enormous. Most theoretical estimates place the number of physical qubits required per error-corrected logical qubit in a surface code at useful error rates in the range of hundreds to thousands. Willow has not demonstrated anything approaching that ratio at useful circuit depths. The threshold crossing is a necessary condition, and necessary conditions are not sufficient ones. Third, the Zuchongzhi sampling lead exists on a benchmark whose history includes at least one prior episode where classical simulation improvement substantially narrowed a claimed supremacy result. Random circuit sampling has been partially eroded by classical advances before, and there is no structural reason the specific margins USTC has claimed are safe from a comparable improvement. The synthesis across those 3 points: the error bet is favored on the physics, favored on peer-reviewed and independently acknowledged evidence, and favored on the metric that fault-tolerant theory requires. The speed bet is ahead on the headline number and holds the compounding strategic asset of fabrication self-sufficiency. The odds sit with the error bet as a meaningful but not commanding favorite because the path from threshold crossing to useful machine is long enough that the speed bet's scale advantage retains live value if commercializing error correction proves harder than the theory suggests. 4 catalysts will price the next move in this race. The first is independent reproduction of Willow's below-threshold scaling by a group not affiliated with Google, whether an academic team or a competing company using a different surface code implementation. If an external team confirms the error rate trajectory reported in December 2024, the one remaining structural objection to Willow's result disappears. The error bet moves from meaningful favorite to heavy favorite. Peer-reviewed plus independently reproduced is the strongest evidence-based quantum computing has seen at any scale. The second catalyst is the next Zuchongzhi generation. If USTC publishes a result that combines a larger qubit count with a measurable improvement in individual qubit fidelity and a first attempt at below-threshold error correction, even a modest one, the clean loss on error correction is partially recovered and the line moves back toward an even contest. If the next Zuchongzhi result again focuses exclusively on sampling depth with no error correction data, the clean loss becomes a structural feature of the platform rather than a temporary gap, and the error bet extends its lead without needing a new result of its own. The third catalyst is a classical simulation result that reproduces or closely approximates USTC's most recent random circuit sampling output using improved tensor network or equivalent techniques. This does not help the error bet win in any direct sense. It changes the question itself, from which quantum bet wins to whether the speed bet is pricing a real advantage at all. If a classical team closes the gap on the latest sampling benchmark, the speed bet's entire value proposition, that the classical frontier has been durably crossed, comes into question. The odds on the speed bet drop sharply on this outcome. The error bet improves by default rather than by its own progress. The fourth and most decisive catalyst is Google Quantum AI publishing a demonstration of an actual error-corrected logical qubit performing a gate operation with fidelity meaningfully above what the underlying physical qubits achieve without correction. The gap between threshold crossing and logical qubit operation is precisely where the error bet's price currently contains most of its uncertainty. If Willow or a successor closes that gap with a peer-reviewed result, the error bet moves from favored on physics to favored on demonstrated capability. The speed bet's sampling headline would at that point be a historical marker rather than a live competitive asset. The evidence as of mid-2025 prices the error bet at roughly 2-to-1 over the speed bet on the question of which roadmap leads to a machine anyone will pay to use. The peer-reviewed threshold crossing is real. The physics argument for why it is necessary is solid. The clean loss on error correction that the speed bet carries is not a gap that closes by scaling qubit count. The speed bet retains live value on 2 specific points: the fabrication self-sufficiency that cannot be disrupted by access restrictions, and the possibility that quantum sampling finds a useful application before fault tolerance arrives, an outcome the field currently rates as unlikely, but has not ruled out. Random circuit sampling remains the shared arena, the benchmark both sides have used, the metric China leads by the public record, and the metric Google's team has argued is a qualifier rather than a prize. The anchor has not moved. What has moved is the weight of evidence on whether clearing that qualifier opens any door the physics actually requires to be opened. The supply chain restriction that pushed USTC toward building its own hardware at scale produced something real: a fabrication capability that compounds independently of Western access, and a qubit count that leads the public record. The constraint became the catalyst. But the catalyst produced a platform optimized for demonstrating that the classical frontier can be crossed. And the race the physics community says determines which machine anyone pays to operate requires something the speed bet has not yet demonstrated it can deliver. The odds currently price the error bet as the more likely winner of that race, with the speed bet holding a lead in a contest whose finish line the field is still debating, and the distance between those 2 finish lines is precisely where the next 12 months of results will settle the price. Which bet would you back with your own capital right now? The speed bet, where China holds the headline qubit count and a fabrication base no sanction can easily undo? Or the error bet, where Google holds the only peer-reviewed result the physics says is a necessary condition for anything useful? Drop your reasoning in the comments. If you want the line updated when the next result lands, whether that is an independent reproduction of Willow, a new Zuchongzhi generation with error correction data, or a classical simulation that changes the question entirely, subscribe and turn on notifications. This channel prices the move when it happens.